1200 and a 0-bit is 600. So very simple bit timing. And this is really kind of slowish. If you were going to send standard bits, you know, and form a byte, you know, to send packets, which you can do, and I've got a project that does that, you know, the baud rate is roughly between 500 and 800 baud, depending on the combination of bits, because you'll see that a 1-bit in total is 1800 microseconds, where a 0-bit is 1200 microseconds in total duration. So you don't have a fixed, even if you have 8 bits in a byte, the timing of a byte can vary depending on the configuration of ones and zeros that make up that byte. And so if we look at the output from an actual remote, so this is a captured remote from this remote that Parallax sells in their IR kit, and it shows the pressing the 0 key on the remote, and you'll see what happens is that we have that start bit, and then we have 1s and 0 bits that follow. And we'll talk about that in how it's made up. But one of the things I want you to notice is that you can see here on the screen, it says AGC. One of the reasons that the Sony IR packet puts out that longest start pulse is that these little infrared receivers have some tuned circuitry in there. So when you start receiving IR, there's what's called automatic gain control that will either pump up the volume, if you will, or knock it down so it doesn't get swamped. So it just has a really clean signal. So the start bit allows for the AGC to settle and be ready so that it can accurately read the rest of the bits. So this is a very typical TV packet. If we look at what's going to come out of a standard TV remote, we're going to get between 3 and 5 packets that will be repeated. Okay, they might have 12. So for example, this guy always puts out 12-bit codes. 15, which you don't see very often, although I have a remote somewhere lost in my apartment that does that, or 20 bits. Now this is a DVD combination, DVD and TV. It's a Sony branded remote, and this we'll see will do 12 and 20-bit output. Because we do repeats, and the reason for the repeats is that there's no feedback. So when you press a button, you know, to point it at the TV, it may miss it, or somebody walks in front, or something happens. So these remotes will tend to output between 3 and 5 packets of the same key. So if I press the 0 button, it has a code that goes out. It'll send it out. I found this remote, the one I got from Parallax, always does 3 times. My Sony remote that does a 20-bit packet does 5 times. So you need to be aware of this when you're using a remote in an application, because every key is always going to, if you're using a standard remote, you're going to get repeats, whether you want them or not. So you might need to consider that and gate for them. So you don't, especially if you're doing kind of an up-down process where you're controlling something, you don't want to have, you know, a double directional change because of a repeat code when you didn't mean that. You just pressed and released the button once. Does that make sense to everybody? Okay, so within the frame that gets sent out, the packet-to-packet timing is 45 milliseconds. So this is something that we can use when we're dealing with timing thing. And typically, if you get a commercial remote, the IR modulation frequency is 40 kilohertz. Now, the IR sensors that Parallax sells are 38 kilohertz, which is really close and will work fine with a 40 kilohertz remote. But there is a cool trick you can do with the variation in frequency that we'll talk about as well. All right, I feel like I'm blasting right through this. No questions from anybody? Okay. Let me just, hang on. All right. if you look inside the packets that you can get, these are how the bits are organized. 12-bit, which we're going to see a lot of today, we always get that start pulse. And then we're going to get 7 bits that is what are called, that's the command that we're sending. So for example, if we just press a button, you know, there is a command associated with that button, and that's what's going to be in those 7 bits. The next 5 bits in a 12-bit system are the device code. As an example, a standard TV remote has a device type or an address of 1. My DVD controller has a different device code. All right. Again, here's the 15 bits. You notice how the commands are always 7 bits, regardless of the bit structure of the packet. In the 15-bit system, we have up to 8 address bits. In the 20-bit system, there's only 5 address bits, but there's an extension of it. There's these extended bits that are used for other things. So these are the packets that you could see, and these times out here are the maximum, it's the maximum duration of that packet. So you can see these all fit within 45 milliseconds. So within the Sony system, from the front end of a start bit to the next start bit is going to be 45 milliseconds. Here is a capture from this remote. It's a button 0 from the TV, and I don't know if you can see it through if it's big enough, but you know, here it says TV 0/10. That's this 0 button. But you can see that this is one frame that happened to be 3 packets that were sent out, and if you look, this says 50 milliseconds where this started. And if we look here, that's at about the 95 millisecond mark. So you can see the 45 millisecond timing from here to here. And so from a safety standpoint, the end of this packet from the first detected to here is going to be 150 milliseconds. But remember, some TV remotes send 5 packets. So you'll see where that comes into play here in just a second. In fact, here's a capture from my DVD remote, and you'll see it's sending 5 20-bit packets. Now, for those who haven't seen me talk about this before, I'm using a little $12 logic analyzer from Amazon, and I've got it connected to a piece of freeware called PulseView. Within PulseView, it has an SIRCS decoder. So in this particular case, in fact, I have it hooked up now live if we, you know, so we can look at some things. But this is PulseView, and as you can see, right now I have P0s connected to my sensor, and then the SIRCS decoder is connected to that pin. So this is showing me the bits that are coming out and what they are. So there's start bit, command 9, address 1, and this all works out to the TV code of button 0, the 10th button.
Hey, John?
Yes.
The SIRC decoding, is that like an option you choose in the tool that says
yes,
that?
so what happens is that, let me move this over. So right here are the protocol decoders, and so it's this button right here, and you can, you know, you can type in names and find it. So there it is. And you double click there, it'll bring it there. And then you click on this and you just assign it to the channel that you want to monitor, and away you go. When it does a capture, it'll automatically do the decode for you.
And that's nice, thank you.
Yeah, it's really handy. Yeah, and again, the total cost of this tool was $12 because that was the cost of the little mini logic analyzer from Amazon. The PulseView software is free and is cross-platform. It runs on Windows, Mac, and Linux. So it's a real handy little tool. So again, getting back, this is our 5 packet. So if you round up and call a packet 50 milliseconds, you'll see a lot of times I will have when I've received a code, I'm going to put a 250 millisecond delay before I allow myself to look for anything else. And the reason for that is if I caught any of these, I just want to make sure enough time has elapsed that I've stopped sending repeat packets. So you'll see that in the code. And here's a blow up of a 20-bit packet. And this shows the things that I had on mine. So again, we have the start bit. Here's our command bits, the address, which are only 5 bits in the 20-bit code. And then we have these extended bits. They tend to always, at least in what I've seen, and I'll show you live, they always seem to be the same. I haven't found anything that explains the details of the extended bits, but perhaps for TV remotes, it's not terribly relevant. Okay, finally, here's that little IR sensor that we were talking about. The middle pin is ground. This pin, if we're looking at the front of the sensor, is our voltage. We're going to use 3.3 volts. It's okay if you hook it up to 5 volts because it's pulled up through a 30K resistor. So that's going to make it safe for the propeller. And then this is our signal input. So this is pulled high internally when the sensor is not active. What's going on in this sensor, if it wasn't clear earlier, so when we press a button on a remote, it's not like turning on a flashlight. We're actually modulating it very quickly. In our case, around 40 kilohertz. This is a smart device. Internally, it has a bandpass filter that is centered on its specific frequency. You can get these in various frequencies. And this chart from the data sheet shows that when you have the center frequency that the part is designed for, that's when you get the best output. So you can see this would be, relative frequency is 1, then your output is 1. So it's maxed out. You'll notice that the bandpass is somewhat narrow. So as you get away from the center frequency, the responsiveness of the sensor drops off. Now, Andy Lindsay exploited this some years ago in a robot project where he did a frequency sweep and then looked for detection. And what that allowed him to do is use the IR sensor as a measuring device. So if you've seen bobots following each other in a train when they're not physically connected, what Andy's done is he's put 2 IR sensors on either side, and he's looking at a plate and the difference between each side of the robot. So when the lead robot turns, if the follower robot is here, this side is going to be at a different distance than this side, and the follower will compensate for that and go with it. I've used this frequency behavior in another application. Again, I'm going to talk about that in a bit. So it is useful to know, but keep in mind, you're going to get the best results out of IR if you're transmitting, and we are going to talk about that, if you transmit on the intended center frequency for the receiver. Okay? Any questions before we jump into the code? Because now we're going to go coding. Oh, I guess we could look at the hookup one more time. So here's that hookup diagram. As you can see, here's the IR sensor. I have a white wire coming over to pin 0. Remember, I always use white for signals. And then this is ground, is the center pin. And then I'm going to 3.3 volts, which I'm getting off a header here for the VCC. And then once I've put the sensor into the board, and then I just twisted it a little bit so that it can kind of see this IR LED. Here, this resistor, I'm using 470 ohms, but anything will work, I'm sure. Anything, between 100 and 1K, probably even, you could probably go higher than that because there's only, an inch and a half between here and there. And so that's going to the anode side, which is the positive side of the IR LED. And then the cathode side, the negative side, is going to ground. So very easy connections. And the later programs that we work with today will be using the IR transmit capability. Okay. If we go back quickly to this slide, you'll remember that the bits coming out of the IR sensor are low-going pulses. And what that suggests is that at the core of any of our code is the ability to measure a low-going pulse. In fact, we've been doing IR. The nice thing about Sony IR is because of the simplicity of its protocol, it's very durable, which makes that really nice. But very simple processors can handle it too, within reason. So way back in the day, and still today, use the basic stamp 2 to decode Sony. And we can do that because the basic stamp 2 has a command or instruction rather called pulse in. And we can say, hey, give me a low going pulse. And knowing what bit timing are, we can build up a word. So the first thing we're going to do, if you look at the code samples I provided in program 1, are you seeing my editor?
Yeah.
Okay. All right. So the first thing we're going to do is learn how to measure a low going pulse. And for the newcomers, I always use a template. If you don't have it, I can get it for you. So all of my programs have a specific look and feel because I start with a specific template. And I have a way that I code. Now, one of those ways is defining time at the top. Since we do a lot of output to a terminal, since those that are using Macs, they can use a terminal too, but the debug system that's built into Propeller tool, I don't know how it works on say FlexProp. So I'm just counting on terminal output for all of my programs these days. If you are using a Mac, change this to TANSI and then you'll be fine using FlexProp. We do have to define an input pin for this first project. So I'm calling it IRN and I'm putting it on pin 0. That matches the diagram we just looked at. And in this case, we're just using code to talk to a terminal, the full duplex serial to talk to the terminal, and we have ANSI support if we need it. So again, for the newcomers, what I will frequently do, I try to do all the time, is to show that like Rome, there are many roads that lead to good programs, and you have a choice. As you develop a feel for programming and within your own experience, your own likes and dislikes, you'll figure out your way. But I, in these courses, tend to show you all the ways that are possible and will suggest one might be better than the other, but do give them all a try. So the first thing we're going to do is measure a low going pulse with this method called get low pulse. And so it is, we're going to pass it a pin. Now, to see how it works, we'll go into it. The first thing that we're going to do is start a loop that will set a counter variable to the system timer. So this is the start of the pulse. What we're doing here is waiting for the start of the pulse. And if I was really clever, and I sometimes am not, what I should have done is this. I should have put here, so add this to your code, pin clear pin. The reason is we don't know the setup of that pin coming into this function, into this method. So that pin clear will remove any other connections that it might have to some smart pin circuitry and set it to input state. So now what we're going to do is sit in a loop, constantly setting T0 to the system timer. And while we reading the input pin, so this pin read tells us the level of the pin. So we're going to stay here as long as the pin reads as 1. Remember, the idle state from the sensor is high. So this is going to wait and just keep resetting T0 while we have no output and we just have the idle state of the IR sensor. Now, when this goes low, we will drop through and now T0 is set to the falling edge of the pulse. And now we have the same loop, just in the other order, where it's going to wait and grab the current timer, the system timer, and put it into result until, it's going to wait while that pulse is low. So as soon as the pulse goes back high, we will drop through. Well, so you see, we've tagged 2 times, the beginning in T0 and the end of the pulse is in result. Well, the width then is the difference between the two. So this line, result minus equals T0, will give us the pulse duration in system ticks. Now, my programs, I tend to run at 200 megahertz. So a system tick is 1/200 millionth of a second. I have a constant here, I have a constant in the program called US001, which is the number of system ticks in 1 microsecond. So what's going to happen is that this is going to grab the width of a pulse, divide it by that constant, which converts system ticks into microseconds, and then we'll display it. So this is a very, very simple program. So if I press F10 and then F12 to bring up, you see I had all kinds of stuff in there already. And I have it armed so that you have to enable the thing and then press a button, and it will tell you to press a key on the remote. So now when I press a button on the remote, you see that I get a number on the screen. It says 2558. Well, that's 2,558 microseconds. These remotes don't use super precision oscillators in them. So the start pulse in this case is a little wider than what we would expect. In theory, that would be in a perfect world, that would be 2400, because that's the start pulse from this Sony remote. Now, I have this set up. You'll notice that after doing all this, we wait 250 milliseconds. Well, remember, a frame could be up to 5 packets of 45 milliseconds. So this 250 millisecond value waits past whatever frame was, as long as I'm not holding down a button. But the idea was it just wanted to measure a pulse, and this gives us, what we expect. So again, for really quick review, we're going to, in here, we wait until the line drops. And just before the line is dropped, we've recorded that time. This waits until the line goes high, and we put that in result. The difference between the two is our start time. Now, again, this is a slow system, so this is fine to work with, for simple things like this. So this could become a pulse in method for anybody that wanted to do that, although it doesn't have any timeout capability like the basic stamp does. But this is the basic mechanics of measuring a pulse, which we need to do to decode Sony. Now, another way to do this is in inline assembly. Now, don't panic if you're new and you're thinking, oh my goodness, assembly, it's scary. It's not. Chip has designed a really, really nice assembly language for the Propeller 1 and especially the Propeller 2. I find, there's a lot of people in the forums, if you go looking around, they'll say, no, I'm just going to write everything in assembly. While I wouldn't do that, I'm now more understanding of the people that say, yeah, I'm just going to do it all in assembly, because the assembly language of the P2 is really, really nice. Now, what I like in particular is that I can mix and match. So I can stick a little bit of assembly into a method like this, and theoretically, we should get a little bit more precision because we're in assembly and we don't have the overhead of the interpreter, in between these instructions. But you'll see this does the same thing as this, just in assembly. Now, of course, I could go back in here and I could, or if I wanted to do this in assembly, what I would do is I would say WX pin 0. Pin. That does the same thing as pin clear, but in assembly. So here we are. This is a repeat loop. I'm grabbing the count, the system counter into T0. I'm test pin is grabbing the contents of the pin and sticking it into the C flag. There are two flags. For those of you who haven't programmed and assembling the propeller, we have a carry flag called C and a 0 flag called Z. And the test pin lets us use either of those flags as a temporary holding space. So this says if the carry flag is set, if it's 1, then jump back to wait 0. So this is it's performing the same function as this while up here, but much faster because this is all happening in assembly. So again, once the sensor goes low, then we are going to, the carry flag will be 0 and this will fall through and we have the starting time of the pulse in T0. Now, again, we're doing the same thing here, but we're waiting for it. The ending, the terminating event for the pulse is not carry, which means it's not a 1 inside, pardon me. If it's not a carry, then we're still in the middle of the pulse, sorry, because it's low. Not carry means 0, so it's low. So while we have a 0, we're going to continue to grab that end time. Once the pulse goes high, we have the carry is back to 1 and we end. And now we're going to subtract, and this is a signed subtraction, the T0 from the result. And because we've declared result as our return value in the method, it goes back to the caller. So it took me far longer to explain that bit of code than it did to write it, I promise you. And as you get used to things, and I'm hoping that you can look here and see here the relationship between the assembly and the spin, because there will be times, spin is really fast, especially in the P2, but there will be times when you really need the speed. And this gives you a way of doing that without having to launch a cog. So if we go up here and change this to PASM, and run this, you see we get similar results. Although a little longer, just a little bit longer, probably because we had that better resolution and we're not dealing with the interpreter. The final way that we can measure a pulse is with a smart pin. So within the smart pin, there is a smart pin function called give me the high ticks, which means how long was that pin high? And I will, and after the pin goes low, then it will give you that duration. Well, in our case though, we want a low pin. So there is a modifier within the constants available that allows us to invert the input. So this is kind of a cool feature because if you look on other bits of hardware, you may have to put a physical inverter in front of the processor to do this. This is putting a virtual inverter in the line. So we've converted a low going pulse that's coming from the outside world to a high going pulse that this will measure for us. So the pin start function takes care of configuring a smart pin. There are X and Y registers that are used by the smart pin. In this particular case, though, we don't need them because there's nothing that they do. This will give us every time we have a falling edge, it will give us the duration of that high going pulse. So what this is doing is the pin read in this case is no longer reading the IO level of the pin. This is the one thing that is a little bit tricky that we have to wrap our heads around. When we assign a normal IO pin, when we say, hey, now you're a smart pin, it's no longer a standard tri-state pin and the behaviors are different. So in this case, when we're using it as a pulse reader, pin read will tell us when it has new data available. So as soon as there's a new value that we can read, then the pin read value will go to 1. So it looks like the pin went high, but it has nothing to do with that. It's actually that the pin is ready to give us information. And now we use the read pin function to get that value out of the pin. And if we go, what did I call that method? SP. Oops. And if we do it again, so you see we're getting the same kind of numbers, a little more than 2550-ish. So there are I've shown you 3 different ways of measuring a pulse. We're going to tend to stick to the assembly way. Now I know that'll seem scary, but you know, if you just accept this code works and you see it, most of the time we're going to be doing that. The reason is we want to be able to measure and verify the codes. So, but there are different ways of doing it. I wanted to show you that. Any questions? Because I just covered a lot of stuff.
John, on the remote itself, it looked like the timing based on the numbers that you showed us were really bad, like 4% or so variance. Are they just using an RC timer to make that pulse?
Yeah, a lot of these, Mike, have 4-bit processors in them with RC oscillators. They're very inexpensive. Although this remote that I got from Parallax apparently pretty popular, because I had a colleague in town last week and went over to his hotel to pick him up, and this was the remote, same remote that they were using at the hotel. So this one gets around, but they are a little wobbly, and it is important to know this. So you'll see the next program that we're going to look at will let us analyze what's coming out of the remote, because we're going to later, as we're going to want to do protocol detection, if you will, and verification, we need to know what kind of range that we have to deal with and what kind of slop we might get out of a remote. And that's the first part of that is this program number 2 that's called IR Analyze. What this is going to do is it's going to grab bits from this stream. I'm calling this capture SIRCS stream, but technically it could be any IR stream in this particular case. And it's going to capture the bits until we think there are no more. Now, this is the tricky part of all of this. So you'll notice, oops, let me go to back to here. In the Sony IR, we always have this 600 microsecond pad after each bit. That's important to know, because if I have this 0 bit, when I'm right here in the code, I don't know if there's another bit coming. So in my Sony IR protocol detectors, I tend to say, look, if I have 900 or 1.5, if you will, 1.5 of these pad periods, if I get that far with no bit coming in, I know I'm done and I can terminate the reception. But this was where, for example, with the basic stamp, we didn't have this opportunity, because the basic stamp, we just had pulse in. And what we would do is we would do pulse in and then grab 13 pulses, because we were counting on using a 12-bit remote. And so then we could look at the pulses. The first one was going to be the start pulse, so we could just get rid of that. And we could verify that the packet we had was in fact a Sony packet by looking for that 2500 microsecond start pulse, or 2400. And then the rest we would just, divide down. But if you had a 20-bit remote and you pointed at the basic stamp, you still only got 12 bits, because that's all we were doing. Now, we had 2 problems there. We didn't have a way of measuring the high time between bits. The other thing that we were concerned about was memory, of course. We don't have a lot of memory in a basic stamp 2. That's not an issue for the Propeller. So the 2 things we do is we grab all the bits, and we actually check this time in between bits so that we know when we're done. We'll see this in a minute. I have one of the programs will let you point any Sony remote at it, and it will tell you the bit count, and then it will show you the packet bits, the same as in the protocol analyzer that you saw in the logic analyzer. When you saw those spelled out, we can do that too, but we have to know how many bits we received. We do that by watching this period here. So going back to this first program, we've set up a buffer called capture. This will let me capture more than we actually need, but this is 32 lows and 32 highs. Because what we're going to do with this bit of code, and I won't get too deep into it because I want to keep us going, but what this does is what we were just doing a moment ago, we were measuring the low time, but then it will also measure the idle time. You can see that's this section here. We're doing the same thing, we're just measuring both. And in the case with this, we want to save those things because we don't know how many bits are coming in. So we're going to pass a pin like we did before. We're going to pass a pointer to where our storage is. So again, for the new people, if you see in my code P underscore, that's a pointer to something or the address of something. So I'm going to pass it the address of this array. Now, they happen to have the same name, but that has nothing to do with anything other than the P underscore says that's a pointer. So you see here, I'm passing that address along to the thing. And then here's what I was just speaking about. We're passing it a timeout period in ticks. Now up here, I've probably made it obnoxious because even though we're doing Sony IR, we may have a different remote that we want to point at this and get a different, we'd get a different value from. So I used a really long period of 5 milliseconds as a timeout. So if the output from the IR sensor stays high for 5 milliseconds, we know we're done and we can then go to the display. So again, this portion will measure the low period. There's a neat trick in here for the newcomers. This is actually a small error in Propeller tool. This PTRB should be highlighted. That's an internal register in the Propeller, and it's a pointer that allows us to write and advance really quickly. So you see what's going on here. I'm writing my time delta, which in this case is going to be the width of the low pulse. And I'm writing it to this, and then I'm advancing it, whatever this size is. So this is actually doing two things at one time for us. In the P1, we would take this variable and have to add another instruction to advance it by whatever this size is. In our case, it's a long, so it's 4 bytes. But this is a really nice feature of the P2. So again, this is 2 sections. This measures the low going bit. This measures the high going bit. And then you can see that when right here, there's a comparison that says, hey, is the time that we've been idle greater than our timeout period? If it is, we jump to exit and we write that final value, which is going to be the timeout value, and away we're done. You'll also notice that we're adding the number of bits. We're counting the bits as we go. So this particular function returns the number of bits that it detected, and it saves them into this array that we passed to it. So if we look at this now, so I'm going to press the 0 key on the remote. And so you see, because it's a Sony TV remote, that's a 12-bit device. So we're going to get 13 bits because remember, always going to get the start bit. And here you can see them. So here's our start bit. This is a 1-bit and this is a 0-bit. And so you can see, as Mike was just talking about with the variation, in an ideal world, this would be 2400, this would be 1200, and this would be 600. You do notice, though, that they are related pretty closely because this is almost 2560, 60, which half of that would be 1280. And then half of that would be 640, which we're a little off down there, but you can see that relationship because probably a simple divider inside. But here, this program allows us to look at what's happening in a remote. Now, here's a Sony branded remote that might have a little better processor in it, but let's see what it does. So it too, now it's a little better. So you see the start bit is 2450. And this is closer to 1200, and that's almost dead on 600. But look, bit to bit, there's even a little bit of variation. So this is important to know when we're doing the protocol decoding. It's not, obviously we're not going to do a comparison of 600 for a bit 0. That's too narrow. We're going to have to give it a range in there. This program allows us to look at a remote, see what the bits that are coming out, and then allow us to fine tune our code. Okay, any questions on this? If you get time to go through and look at this, you'll see it's pretty sensible. Okay, now knowing the bit measurements of Sony IR, we can modify that to give us a value. So this is a very similar program, but we're going to analyze the value. I'm going to press the 1 key now. And so this program is going through and telling us what it thinks those bits are. So this allows me to do the real fine tuning, because I can go through here and look, and you'll see what's going on in here is that we're doing the same kind of thing. We're capturing the stream, same as we did before. And if we have something from the stream, then we're going to loop through those bits, convert their raw time into microseconds, and then we're going to create a display. Now, you see here, I'm using a case statement to tell me what the bits are. So you can see I'm using a pretty broad range here for a start bit. I'm going from 2200 microseconds to 2600 microseconds. And same way with the others. If we get something that is out of those ranges, there's a problem. And we can show that too. Question?
John, when you showed the original slide of the protocol, it looked like the first several bits were command, the second packets was it value? Yeah. It's
called address. It's a device. So think of it as a device ID. So this remote will always have a device ID. These second 5 bits of 1, that's the TV.
All right.
This DVD remote has a different device address.
Of course. So what you decoded was basically a 0, all zeros in the first one, and then a 1, or was it the other way around?
Yeah, it was. No, it was, Mike, because you can see the 1 is right here. So these are LSB first, these values. Okay. And so the 1 in this 5-bit field is going to be the address 1, which is again a TV remote. And then the buttons on the keypad of in the 12-bit code, the number pads are the code for them, or the command for them is the number that's on the key minus 1. So when we press the 1 button, we get the 0 in the command field.
What do you get when you press 0?
You get 9. So it acts like 10. Yeah, in fact, this slide that you can see, and maybe I can zoom in on this. This is that button. This is a 9 button being pressed. You can see here's the 9, 1001 in that, and it says command 9, but here's what it is on the remote. It's either TV 0 button or 10. Does that answer your question, Mike?
Yep, that's it.
Okay. Yeah, and you'll see these codes are all known. In fact, I have one of the later projects, I took a big database of Sony TV codes and I stuck it into its own object. It makes it really easy to take a code, pass it in, and get a string back of what that is. Now, we'll see that here in the next program. The final
So,
kind of,
I
go
got a
ahead.
question about the address.
Yeah.
When you have a multifunction controller that controls your TV and your Sony VCR, does it append that address to a 1 and a 0 depending on what the remote wants to talk to?
Yes. Yeah. So you'll have, for example, with this remote, which is a DVD remote and can control a TV as well. No matter what mode I'm in, when I press 1, I'm always going to get zeros in the command field, but the address field will be different. So that way, when a TV won't respond to the 1, but the DVD player will if it's in DVD mode.
Okay.
So, and remember, and I probably wasn't very clear on this, but this started as a wired protocol. So there was a time back in the 90s when you could have from a controller a wire going out. It's just a simple pulled up wire to go to multiple devices, and you could select the device and then select a command. That goes out to all of the devices. All of them on this multi-drop bus will see the command, but they would only respond if their address matched. That protocol was carried over in the IR remotes as well. This is what allows a multi-function remote to operate, because the same commands can go to different addresses, and we can select that by, for example, on this remote, there's a button here that says TV video. So that selects the mode. Okay, and here I can show you that. So here's kind of the final, step in the way as we build things. And again, for those of you that are new, I tend to do things very incrementally. So as you saw, we started with, let's just measure a pulse. Let's look at a pulse stream. Let's analyze a pulse stream. And now we have a practical program that can convert inputs from the remote into text messages that tell us what that button was. So if we run this program, now I'm going to press the buttons in order. So this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 0. So you can see the codes in there for those of you that are good at binary, and I expect everybody is. You can see that the number, if you treat this as 10, then the command is that whatever that number is -1. Now, here is the DVD remote. Can anybody tell me what button I pressed on the DVD remote? See, this is a 20-bit. Ken will buy you a popsicle, whoever answers.
Send you a t-shirt.
Nobody cares about popsicles, I guess.
It's the 1.
I would say
Yes,
1.
I press the 1. Yes, because you see the command is 0, which is a 1 button.
Yeah.
Now, you're probably asking, why didn't you just put that on the screen, McPhalen? Well, the reason is my program only has a database for TV codes. I don't assume that they're the same, so I don't show it if it's not a TV code. But yes, this is a 1. So you can see command is the same, but here's the TV address. Here is the address for the DVD device. And you can see this is a 20-bit code, and here are those extended bits. So if I go through and press the buttons in order, like I did before, you can see the same thing. Now, if I press that TV, here's an interesting thing, that TV video, that is a known command in the TV world. That's why that string shows up that says TV video. And there's the command for it. And of course, there's, things, oh, this is up and down. If I'm back to this guy, there's a channel up, channel down, volume up, volume down. Excuse me, there's a mute button in the middle of this. There's an enter button, and also on here it says previous channel. In the database it says jump or last, which is the same as previous channel. But this little program shows how to decode, and it uses an object. So if you look here, I've taken all of the Sony IRS stuff, SIRCS stuff, and I've stuck it into its own object. This can get a little, hairy, not, but I think if you'll take your time and go through it, you'll see what I'm doing. You'll remember that relationship we talked about with the start bit is 2400, then we have a 1 bit is 1200, then a 0 bit is 600. We take advantage of that. So I only pass to the assembly portion of this program the number of ticks in a start bit. Everything is based on that. But remember, the timing is not perfect. So in this particular case, I'm using 15/16 as my low value for my start bit. And then I take that and divide it by 2 to get a 1 bit, and divided that by 4 to get a 0 bit. So I decided in this that I'm using 15/16 of the nominal time. Why did I use 15/16? Because it was really easy to do in the P2. I can use the QMul instruction to multiply the start ticks by 15. This gives me the result of that. And then shifting a value right in assembly is the same as dividing by 16. And we do the same thing. Now we have in here, no bit is that 1.5 bit periods of 1.5 pad periods, I should say. And then I have a bad bit period, which is a low going period that's too long. And that is the case. And I guess I should stop dilly-dallying. So here's a giant IR remote that I've written a lot of code for, about 10 or 15,000 lines of code. This is a laser tag gun. This particular device, which is P1 powered, uses Sony IR bits. It doesn't use the Sony IR protocol, but it uses Sony IR bit timing to send laser tag information. And there's many things we can do. So for example, I can, shoot somebody, and that sends a coded bullet to the other player. And you think, well, why do we need a coded bullet? Well, I think my friend Dexter is online. So he and I have worked together in this stuff. If Dexter shoots me, then I know who just shot me. And then if he defeats me, then there's an XP radio. For those of you that want to know about XP, we talked about that a month ago. And the XP radio will send a message back to the scoring system that says, hey, Dexter just defeated John. And so we need to know the bullet packet's not just an IR pulse, it's actually who sent it and how much power. There's settings in the tagger. We call these taggers. There's settings in the tagger that say how much energy the bullet has, what team we're on, what field we're on. We can actually have multiple fields. And so that's part of the IR packet so that they don't cross, you don't want to cross streams, just like in Ghostbusters, you don't do that. The other thing we can do is send command packets. You can have, when you're playing laser tag, you have people on the field called referees that can do things with the tagger. So for example, if somebody's misbehaving, you can do what's called a penalty kill, and you can actually, the referee can take the player out and make them have to go back to their base to respawn. We can also send really big packets, relatively, where the referee tagger can say, okay, I want, John's tagger to be, this configuration, and then do a cloning. So that sends a long packet to the tagger. My tagger, if it validates the packet and says, yeah, everything came through fine, will accept the new settings. So this is a real world application of all of this Sony IR stuff that is beyond TV remotes. And it works really well. An interesting thing for those of you that wonder, well, how far can we transmit with this stuff? Now, these guys will transmit across your living room with no trouble. In fact, if you're cheeky. Now, I live in a typical LA apartment with white walls. I could, you know, point this over my head at the wall behind me and still turn on the TV. These are pretty powerful. This guy will go about 1,200 feet. And the way that we're able to do that is we're pumping a gigantic amount of energy through the LED, as much as it will take. And because we're using the propeller, the center frequency that we're transmitting is right on what the sensor wants to have. In fact, when the propeller version of this was first available to the original owner of the company, he did a side-by-side distance comparison of the original PIC-based tagger and the propeller-based tagger. And the propeller tagger exceeded the distance of the PIC by a very, very long distance. The reason behind that, after I got in with an oscilloscope to find out, is that the PIC, you know, nice little processor, but the way that it does frequency generation is not as precise as what the propeller can do. So even though in the case with the taggers, we're using 56 kilohertz, the frequency that was being generated by the PIC was a little bit off of that. And you'll remember from that diagram, that slope, you know, is fairly steep. So the farther you get away from the center frequency, the less sensitive your receiver is. And in fact, we use that in the tagger. There are two settings. There's an indoor-outdoor setting that is completely current-based. So we have two FETs that will switch things in the IR circuit. One of them does the modulation, so we can modulate it and send the output. The second one will either allow another resistor in line or bypass it. When it bypasses it, we allow more current through the LED. So that's our high power mode. So there are actually two outputs in the tagger to do the IR. But again, we're pumping about an amp through the diode when it's on. Now it's on for a very, very short period of time and it can handle it. And remember these pulses, you know, the longest pulse that we're sending is 2.5 milliseconds. Now getting back to this and why I was talking about measuring timing, when we have a TV remote, it's pretty low bandwidth. You know, we're pressing a channel or we're doing something, but out on, you know, when we're playing laser tag, these things can shoot 800 rounds a minute. And now imagine you have 100 players that are all shooting at each other. That's lots of IR signals. And so what the taggers have to do from a reliability standpoint is measure all the bits coming in, because if we have two signals arrive coincidentally, they're going to get scrambled, and we don't want to misinterpret that. So these taggers have a sound effect built in. We also use the propeller to play wave files, so these have really nice sounds coming out of them. So there's a, you know, that old West sound, you know, when a bullet goes by, it goes pa-ching, you know, it's the bullet whizzing by your head. That's what this does when you get a scrambled signal. So it means, hey, somebody's shooting at you, but, you know, lucky you, things were scrambled and we couldn't determine who it was, but be warned. That's a real world use of all of this timing stuff that we're doing here. So you'll see in this code, we're setting up all of that timing. And I'm just going to just review this briefly. What this does when you've enabled the IR sensor, it says, okay, go grab the first pulse you see. If it's not a start pulse, then we know that we jumped in right in the middle of a transmission and we're going to throw that away. So the idea is we wait until a start pulse comes in, and then we grab the next series of bits, monitoring them, you know, validating their length and comparing them until we get our timeout. And then we report to the user that we're done. So if we look at the top level code, one final thing, sorry, and this is a reliability thing. On this particular tagger, this one now has those same IR sensors. You probably can't see through the camera, but those little IR sensors we're using, we have two of them in here, so we have full directional coverage. The nice thing about these, you remember they go low, so they're just wired together because it's a wired OR system. We also have right here a head sensor port. So when the players are playing, they wear a headband with LEDs on it so that they light up when that happens. Well, back in the old days when we didn't have a sensor on the tagger, cheaters would pull out their cable and disconnect their IR sensor, because the headband also has IR sensors in it. And so the code has the ability to detect that. And I have that in here. So if you have an application where you want to check, in fact, I'll do it on mine. Where this comes into play is going back to what I told you a while ago about the sensor. Internally, there is a 30K pull-up on the output. So the output when it's idle should be at VCC through a 30K. The propeller, thankfully, P2, has a 150K pull down capability. Well, if you do the math, if you put 30K and 150K and you put 3.3 volts between them, that center point is going to be somewhere a little above 2 volts, which is well above our threshold, our input threshold of 1.65 volts. So we can do that. And what it allows us to do is detect if the sensor is missing. So you see, I have that right here. I have a constant that says, hey, do I want to check for that? And I am doing that. And in the sensor check method, it will look for a certain period, for 3 milliseconds, I think it is, because we should never have a start pulse should never be longer than 3 milliseconds. I mean, it's supposed to be 2.4, right? So if the input is low for 3 milliseconds, then I know we have a problem. And I can do that. So if I run this program again, so it's ready to go. Now I'm going to rerun it after I pull the sensor out of the board. And it made me a liar. Why? I will have to get back to everybody because I know this works. At any rate, in the taggers, because we're using P1s, we actually have a pull down resistor. So I will check on that. Forgive me. Doggone it. I hate when a demo goes wrong. But there is a mechanism that we use in here because it's critical to know that we have a sensor. I'll correct that and I'll repost the code later. I'm not sure why that check failed because I had checked it 2 weeks ago. At any rate, any questions on transmission at all? I know it got kind of fast and furious.
John, on the analysis, I guess number 3, program number 3, other comes up as error.
Yeah.
Can you elaborate on that a little bit?
Well, other is a bit timing that we didn't expect.
I've got 4 remotes here and every one of them comes up error.
Well, then what I would suggest, Carol, is go back to version 2 and see what your bit timing is. Now, make sure too, is it a Sony remote or is it a, because these are universal remotes. I didn't talk to that. I made the assumption everybody that had one of these remotes from Parallax had the documentation that showed how to set it to Sony mode. If you use program 2, okay, that just gives you raw numbers out. So here's a Sony remote, and you can see now, I think I have a little, so here's a little remote control from Amazon that comes with an IR sensor. I'm pretty sure this is not Sony protocol. And you can see that I get a whole bunch more bits out of the thing than.
Yeah, I'm getting 33 bits.
Yes, so it's not, that remote is not set up for Sony.
Okay. Yeah, it was the only universal I had. The rest was proprietary.
So what I would suggest you do is open the battery compartment and get I have found that in remotes, the battery compartment usually will have a label that has the product number on it. And I have had really good luck finding for universal remotes, the documentation that tells how to set up for Sony. But you can see here, remember in the Sony world, we expect the first bit to be 2400 microseconds with a 600 microsecond pad. This little dude has, 9 milliseconds followed by a 4.5 millisecond pad.
Yeah, I got one of them, and it comes up with the thing. Shows error. And then my universal RCA. So
I'm sorry, I wasn't terribly clear. The reason for this program too is so you can figure out what's going on with your remote. I mean, later, if people are interested, we could do, there's another protocol from Philips called RC5 and a derivative called RC6. It uses different bit timing. I suspect that that's what this is RC5.
okay.
I'd have to go look at it. But when you're for Sony, you should always have a low period. You're going to have one of three values. Your low period is always going to be around 2400, around 1200, or around 600. And then the high period that follows is always going to be around 600. This particular case means we timed out. So we had this 600, and then I allowed for a long timeout in this. I said, hey, if nothing shows up for 5 milliseconds, then we're done. So you can see that the timeout period I said of 5 milliseconds is what we get for the last high period.
So on that one, that's basically a 1 and 7 zeros and another 1 and 5 zeros.
Yes, in this case, yeah, because so here's the start pulse, and here's 1, 2, 3, 4, 5, 6, 7, because so there's 7 zeros, that's command 0, because this is a Sony remote, this first one up here. And so that's command 0, which was the 1 button. And then there's a 1 and 4 more zeros. That's 1. Remember, these are LSB first. So this is the LSB. And the TV code is 1. So this is what for this version of the program, this is initially this is version 2. That's why I called it IR analyze, because it's, hey, we don't know what we have. This will just show us bit values so that we can figure out what it is. Now, one of the things that I probably need to do is I would suggest on this program too, changing this to 128, because this little remote said 33 bits. Well, we only had enough for 32 bits, which meant we were cutting into our code somewhere, and we were probably clobbering our code without knowing it. So we'll just change this to read up to 64 bits.
So on the RX demo, once we figure out what our spacing is, are there numbers in that demo that we would change to match our remote?
Yeah, so, or just check to see, I mean, they should, hopefully what the values that I'm using are going to be fairly generic, but do have a check. The nice thing is, again, writing the code for this guy, I have it lucky in a way because I'm writing the transmit and receive code. So the transmit bits are dead on, because we're using a propeller at 80 megahertz and we're doing that in its own cog. The other advantage of this version over the previous PIC version is that in the PIC version, the IR sensor was connected to an interrupt pin. So no matter what was going on within the processor, if somebody shot at you, there was an interrupt got generated, and that would often clobber other processes. Well, in this guy, I have an IR transmit cog and an IR receive cog. So I can shoot and get shot at the same time without any problems. And because the propeller is generating the timing and the modulation frequency, we get really precise range, and I know what's coming out of the tagger, so that I don't have to be so sloppy on my checks. I give it a little bit of wobble, but not very much in this, because the propeller is generating really precise intervals and modulation.
Yeah, on the demo, mine won't show up anything. It registers on the first 3 programs, but when it gets to the demo, it's like I'm not even pushing a button.
Now, if you're looking at it with either program 2 or 3, are you getting just Sony? Are you getting what looks like it could be Sony IR bits?
I'll run it again here.
So if you have bits that are not 600, 1200, or 2400, then it's not a Sony IR stream.
I would. So the demo only works with the Sony.
Yes, sorry, yeah. So
That explains it. Yeah.
Program 2 doesn't care. Program 3 is saying, hey, I'm assuming I have a Sony stream and I'm looking at that. Program 4 is doing the same thing.
I get a low of 662 and a high of around 1500.
That's pretty high. I've never seen a 1-bit that high. But you could certainly
4588 and high 4360.
Yeah, that's not Sony.
Okay, I'll let you go, John. I just wanted to clarify that.
Okay. So once you again, look inside the battery compartment, get the ID off your remote. If it's a multifunction remote, look it up and then get the code. For example, on this guy, there's a button right here that says setup. So you press that until the little LED turns red, and then you'll punch in a code that corresponds to Sony. The documentation for this guy, if you have this one from Parallax, it's on their website. It comes with it, but they also make it available as a PDF.
Thanks, John.
You're welcome. Okay. So now that we have, again, we're dealing with Sony remotes, we can do something functional with it. I talked about laser tag, but we can do something where we can turn our an inexpensive TV remote control into just a command and control device. This first version is really simplistic in that it will take the buttons, the number buttons, and toggle them. So you'll notice if I press right now it says everything is off. If I press the 0 key, then it will toggle on and off, and any number. So this is pretty straightforward. The way that it works is that it looks for an IR code, and here this is one of the ways that even though this is intended for Sony, we want to make sure that this is a bit of validation. Sony packets are always 12 bits, 15 bits, or 20 bits. And it's usually the outer two. You don't see 15-bit very often. So that's kind of a check. And then it looks at the command. You can see we extracted the command from the code that came back. Again, it says lower 7 bits. For those of you new to the Propeller, this dot notation allows me to grab bits out of a value. So what I'm doing is I'm grabbing bit 6 through bit 0 and putting that into this variable called CMD for command. All right, and now I'm checking here to make sure they match up with these constants I have. So here are my buttons for the, those are the command codes that correspond to this and to this. It works with both remotes because I'm not looking at the device code with this particular thing. When we do get a valid button, then what happens is we turn on an LED, you'll notice a flash on your edge board. And then it will fix the bit alignment. Remember, button 1 says it actually comes back as 0. So what I'm doing is, since I'm looking at the command values, I'm adding 1 to that. And if it's greater than 9, because I pressed the 0 button, which comes back as 9, now I add 1 to that, that's 10, that will make it 0. So these 2 lines of code are just fixing that bit alignment thing with the number keys. And then I will toggle the bit. So this exclusive or equals, that will take the bit within this dev status. So this word is the 16-bit value. I'm only controlling 10 things here, if you will, but so I'm using a word to hold those bits. And so we just toggle the bit and then refresh the outputs. In this particular case, refresh the outputs just displays the screen. Now in a real world device, we would hook up, we would assign pins to each of our functions and we would turn things on or off. So we could have lights or light shows or any kind of thing that we wanted. The other thing that I added for fun in this, if we go back to the screen, I've got things on and off. If I press the power button, it shuts everything off at once. So very, very simple, but you know, small world practical thing. You can turn a remote control into a lighting controller for your house, or, you know, turn on some music, turn on some mood lights, some faux candles, and, you know, have a romantic evening with your loved ones, whatever you want to do. Did a second version of that that is analog-ish. You know, there are the volume level on a TV is an analog thing, right? We raise the volume or we lower the volume. So I use that in the second version of this program. Now in this particular case, the output shows the channel number and there's a little indicator to which one I'm pointing to. So if I use the channel up and down key, you see the little cursor moves. And so I can select if I want to modify output 7, then I can, with the volume up, I raise it. I use 5 as an increment here, and I think I go to 100%. Yeah, and then up and down. But very easy. But this is a simple little program, and it shows you how to select something and then modify it. So that might be of interest to people that are doing little UIs. I'm doing it through the screen, but you could certainly also do this on an LCD or a you know, an OLED display or whatever. Okay. And again, this is doing same kind of thing with constants for the keys that we want to change. This LVL delta, that's level delta, that's how much the up and down arrow keys will change our value. In this particular case, we're not using a bit field, we're using a byte array of 10 values. Since we're only storing 0 to 100, we can store that in a byte. So we've got 10 of those, 1 for each key. And we're doing the same kind of process here, where this looks a little peculiar where it says button 1 to button 0, but remember button 0 really could be called button 10. So that's kind of 1 to 10. And this does the same thing where in our case, when we have a, let me go back to the screen. I was changing the keys. I was changing the keys with the up down buttons on there, but you can also do it direct. If I press the 8 button on the keypad, you'll see that it goes directly to 8. So I have direct access to any channel. And I can also scroll through them with the up down arrow, up down channel keys. And then once I'm on a particular channel, I can change its value. And I can also, so you see, let me get a couple values in there. By the same token, if I do power, then I clear everything. So again, simple little controller, but you know, it's taking a $5 remote control and putting it to use. Remember, we're only using, one cog and very little horsepower to do all this process. So this could be part of a much larger control system. Any questions on IR, Sony IR receiving? This has been a quiet group today, other than
Yeah, John, I got a question about
yes, sir.
Your when you press a button once, you send out 3 identical frames, or 3 or 4 identical frames, because you have no feedback and no error correction. Is that
right?
Is that correct?
Yes. Yeah. I just for terms, I refer to the entire transmission as a frame, and then there are packets within the frame. So in my definitions, I every time I press a button, I get a frame. With this remote, I found that each frame is 3 packets. With this remote, I find that each frame is 5 packets, and you'll see that as you read, you know, the interesting thing is Sony never officially published the SIRCS protocol. This has been derived by people like us.
So your packet, let's say you've sent 3 packets, your code here will respond to the first valid packet. Let's say
Yes.
that your first packet is corrupted and it doesn't compare to any of the button presses. So
Right.
it negates that. Then the second one, or the second packet, is a number that jives with the command, and it takes that as a valid command.
Yes, and then you'll notice in all of my handlers, when I get a valid command, I throw in a 1/4 of a second wait, because that would get me past all of the other packets in the frame.
So how does that, when you hold the button down continuously, it's got to go, it gets its first command, it processes that, it idles out, and then it'll respond to the next stream or next packet, which is identical because you've holding down the button.
Yes, now I'm going to be ignoring it for 250 milliseconds. So this is going to chop things up, but here I'll do that. So we're on channel 8 on this right now, and I'm going to hold the volume up, and I'm going to press and hold it. So you'll see it's incrementing up at about 1/4 of a second rate. So I can control the change rate of things by changing that delay of looking at things. One of the things that I didn't talk about that might help clarify this is that my IR receiver, the Sony IR receiver, is a single shot device. Once it gets a valid code, it says, I have a code, and it ignores everything that comes after that until you grab the code. That's why here, you see where it says IR enable, I need to do that to clear anything that's old, that's in the buffer, and tell the background to start looking for a new packet. So I don't, because of the way TV remotes work, I've not, in my experience, found it necessary to buffer multiple packets in. Once we get one, we know this is a slow process and there's going to be more of that, so we can ignore everything else till the master program has had time to process what we did receive.
All right, thanks.
The Sony remote. Now with the tagger, this is a little bit different because I actually have, in this, we're using Sony IR bits, but we're not using the Sony IR protocol. What I was saying earlier, so this can do, there's kind of 3 things that we can do. We can shoot, you know, I press the trigger, we shoot a packet. That's 15 bits. Now this is a legacy thing that I had to match up from the old system. So what happens is that I have to receive in a number of bits to determine whether or not the packet is a shot packet or a data packet. And I can do that. Once the data packet comes, once I know what it is, I can alert the foreground in 2 different ways. There are 2 different data packets, though. There are what we call referee packets. So again, if a kid's out on the field and he's struggling because he's getting shot a lot, what I'll probably do is give him extra life points. So that's one of the commands I can dial up here. There's a little user interface here, and I can shoot him and give him extra points. So that's usually a 3-byte packet. If I want to use this and I want to transfer settings to another tagger to make it do something different, that's a clone packet. That's about a 45-byte packet. And so in that particular case, we still use the start bit. And then after that, there is a single shot buffer that will buffer in the bytes. And then I pass to the foreground, just like in this code, I passed to the foreground a bit count. In the tagger, I pass a byte count. And the byte count will tell me what's going on. Because what I end up doing is converting the 15-bit bullet packet to 2 bytes. And so I tell the foreground it's 2 bytes. And that way it knows, okay, process that as a bullet packet. If it's 3 bytes, it knows to process it as a referee command. If it's 45 bytes, it knows that it's a data packet with new tagger settings, and it takes that I have some things that I've done. One of the things we did to make this more reliable is that we used, for those of you that were on when we did the one wire protocol, you'll remember the one wire protocol has a CRC value in it. I actually used that CRC method from one wire. I stuck it into the IR packet here because we are sending IR, in the outdoors. And so when we send a clone packet over, it includes a CRC. And so it's made the system far more reliable than the previous system. We know that, if it came over, then we know everything's good, including the CRC. And in fact, when we can do a lot of those same things like with the cloning through the wireless system, because the XB CRC is kind of weak, to be candid, on the upper layer. Underneath, it's probably really good, but we essentially take our IR packet and just put that into an XB packet. So we've got the XB layer of protection, then we've got our layer of protection, including the CRC. What that's allowed us to do is have a really reliable system going from the PIC to the propeller. So the key to all this, the underlying lesson is that if you're doing a bit-oriented thing like this, you'll notice that the IRRX, and that's redundant. Sorry. So I'm going to show you this is actually a redundant code. I ran into this. IRRX will enable the IR and then wait for something to come in. So this is blocking code right here. And that's why you didn't need that IR enable, because IRRX re-enables the system. But you'll notice that because it's a P2 and we can return multiple results, we're returning the code, which are the bits, and then how many of them there are. So we're returning 2 values from the IRRX method. And in this particular case, we only care about the command code, so we extract that. We're using the bits just as a verification that it is probably a Sony thing, and then we process it. And here you notice we're looking for valid command codes. If it falls outside of any of these things, then we just ignore it. And then the key to ignoring the repeat packets within a frame is that delay right there. Okay.
John, that's 250 milliseconds. Did you mean 25 or 250?
No, 250, because each packet mic is 45 milliseconds.
Oh.
Yeah, so if we go back here, if we look at I think where one of these multi-packets are, so here's the IR capture from the Sony remote. So right here, this start bit is at the 50 millisecond mark, and you can see here this next one, here's 90 milliseconds there. So because of quantization, it looks like it's at 96. So between here and here is 45-ish, 46 milliseconds. So this is one frame period, because remember, this is a 12-bit frame. Here is a 20-bit frame, and you can see, well, this one actually looks better. So you can see here's at 100 millisecond, this 0 point, and here where this drops that's 140, that's 145. So leading edge to leading edge of the start bit is 45 milliseconds in the Sony system. Since you can have up to 5 packets, I just rounded up. Instead of multiplying 5 by 45, I just said 5 times 50 and 250. And it's obviously, gives me even a little more leeway technically, because we don't get the first value until about this time frame. So if we receive a value here and then wait 250 milliseconds, we're going to be somewhere out here, before we'll even think about looking at another button. But that gives you, from a human standpoint, time to press and release the button without any problems. Okay, Jim, I saw you unmuted yourself. What's the question?
Oh, no.
Oh, sorry. It's been a quiet group today. I was all excited. I thought, wow, there's going to be all kinds of stuff, but it's been quiet. Perhaps this is too easy.
So John,
Yes.
you have that 250 millisecond block. If we were doing a performance version of this, to think about that, what we'd really be doing is timing out for the remainder of the time we didn't see data in the current frame. And then starting our listening again.
Well, you'd have to have a longer timeout, Stephen, because you can see here's the idle time between packets within the frame. And again, going back, here's a 12-bit. Well, it has a longer period. So technically, one way you could do, since 12 bits is going to be the shortest packet, you could say to yourself, okay, if I have a 12-bit packet that's all zeros, how long is that? And what is this idle period going to be? And that you could do it that way. I tend to time out right, again, 1.5 pad periods, and then I ignore anything coming in.
Gotcha, I was misreading that.
Just for,
I thought
just
you
for
were
TV remotes.
right. I thought you were using that for frame timeout, not packet timeout.
Say again?
I thought you were using that for frame timeout, not packet timeout.
Well, technically I am, because I know that within a frame, again, that's one of the things about Sony, is that it repeats the packet n times per frame. Other remotes will actually are different. They send a code, and then if you keep holding the button, they send a repeat code. So you have to keep track of your last input. Again, this is what makes Sony really nice and easy to use. It tells you every time what it wants to be. So as soon as I have a valid code, I say, okay, I'm going to ignore the IR for 250 milliseconds. That gives me plenty of time to release a button. Now, as in the case where I demonstrated a minute ago, when I press and held the button, so now the remote just sending out stuff all the time. What that delay does is just provides a timing of how fast or slow I increment or decrement.
Yep, that makes sense.
It's a tricky thing because you don't want to have it too long because it is blocking. But in this particular case, this is a low bandwidth kind of thing when we're pressing and releasing buttons. So 1/4 of a second from a human standpoint doesn't even feel like it's there.
Yeah, agreed.
You notice that when you're pressing and holding the volume up or down, it ramps at a specific rate that is based on that delay.
Good. Okay, thank you.
Okay, you're welcome. Okay, I guess we'll go to the final stage, which is actually the easiest part, which is transmitting. So let me go back to my. So with transmitting, Sony, we now, for those bit periods, we have to modulate the output. So we have to have an oscillator, if you will. So for a start bit, we have to oscillate the pin at around 40 kilohertz. In our case, we're going to use 38 because that's what the sensor wants, for 2400 microseconds. Then we're going to turn it off and we're going to let it rest for 600 microseconds. For a 1-bit, we're going to do 1200 of oscillation and same rest period. And then for a 0-bit, we're going to do 600 of oscillation. So the key is being able to oscillate a pin. The best way to do that, so we're going to skip right to it, in my opinion, the best way in my opinion, so we're going to skip right to it, is to use a smart pin in NCO frequency mode. Now, in this mode, the smart pin becomes an oscillator with a 50% duty cycle, and you can have very precise frequencies here. Another way that you could do this, in fact, I did this for those of you that read my first P2 article in Nuts and Bolts. I think I used PWM to do that. That works too for low frequencies, but when you get into higher frequencies, NCO frequency mode is a better way to go, in my opinion. And so here is a capture of an output from the propeller. And these gray areas, I don't know if I can zoom in enough. Yeah, well, I didn't have that, but I can do a capture because I have the system hooked up live. But this is the pin oscillating. Now, so this is an active high signal, which is why we are connecting it to the anode of the LED. So when we want to output a bit, so you can see here's a start bit, and that I'm going for 2400 microseconds, and I'm oscillating at whatever frequency that I want. And then I shut that off because that's that rest period between the bits. Here's a 1 bit, here's a 0 bit. So which one of you clever people wants another ice cream from Ken can tell me what key was generated this code? That'll give me time to open up another can of water.
It looked to me like an 8. Am I right?
Or is that a 0?
It's a 0. Yeah, because you can see 1, 0, 0, 1. So this is 9, but remember, it's off by 1, and then this is a TV remote. Here's 1, 0, 0, 0, 0.
I will forever be amused that 0 is 9 and
Yes.
1 is 0 and etc.
Yes. Well, if you look, in fact, I'll show you something in the Sony IRS, this analysis program. I found a database that has just a bunch of key codes on there. So you can look, there's a bunch of things that it can identify. I probably don't have enough remotes at home to do that. Now, the ones that I've commented out are because on that webpage, it said they were, what am I trying to say? Retired, that nobody's using those codes anymore. So this is a really simple linear search. The way that this code works is it points to the beginning, and you'll see that each of these codes is, each of these lines is a code, and then a string version. That's why there's a terminating 0. This is a string. And so what happens is it points at the code and it reads it and says, is that a match? If it is, then it just increments a pointer and it prints that string. This 0 ends it right there. If it isn't, then I use, you can see it right here, I advance by the string size of this. So what that'll do is skip over this to the next code, but it's linear. Now, again, with this kind of program, you'd never notice how slow it is if you were at a code down in the end. So this is not ideal for everything, but it works out fine for this simple ID. Now, I've actually, in an end program here, I've taken all of this stuff and put it into its own object so it's easier to deploy.
Great, nice.
So here is the initial stuff. What we're going to do, again, is we're going to turn on an oscillator on the pin using NCO frequency mode. So here I have a little method that is doing that, where it's saying, hey, if your frequency is greater than 0, I'm using 0 to turn off the oscillator on a given pin. Then what it will do is it will select NCO frequency mode. For those of you new to smart pins, this P_OE says, hey, this is an output pin, so we need to enable the output. We'd think, well, it's an oscillator, but you have to manually specify that. If the pin needs to be an output, then you have to tell it right there. So we add that in. I can tell you what's happening. It's a little hard to explain why, but here's what's going on. The X value of the smart pin, it says on every clock cycle, which in my case is 200 megahertz, add in this number. What it will do is it will then, it adds that in, to an internal accumulator, and it will put bit 31 of that accumulator onto the output. Now, this is a peculiar thing where we're taking the output frequency that we want. This frac instruction will take this value, shift it by 32 bits, and divide by that value. Now, the result is when I add whatever that number is into an accumulator on every cycle and then look at bit 31 of that accumulator, this frequency is created. Now, you can actually, and I did it this morning, and if you want, do it easy with yourself, do a pretend 4-bit accumulator and then put a number, like a 3-bit number in there and add it in. And whatever is in bit 3 of the accumulator, you show your output. You'll notice you'll always get a 50% duty cycle, but your frequency will be dependent on this number. The bigger this is, the lower the frequency. Now, the reason I prefer this, as I said earlier, over, say, using the PWM smart pin mode, is that in PWM smart pin, we only have 16 bits. In this, we have 31 bits, so we can get finer granularity. In fact, for some musical kind of things where I need beeps and boops, but I want them to match musical notes, I set this value to 10, and then I multiply my desired frequency by tenths because I'm specifying it in tenths. So that way I can get 1/10 of a hertz. So I have a music program somewhere that does that, where I have all the musical notes on a piano in there to 1/10 of a hertz resolution, and I can play them. Now, it sounds a little buzzy because it's square waves, but for beeps and boops, I can do, for little simplistic games, I can do, the little charge ditty. And I made my friend Emlyn for DEF CON 1 year, because this is derived from the P1. The P1 can do this too. But we made her a backpack. She's a very big Star Wars fan, so she could press a button and the propeller would play the Emperor's March. She likes Darth Vader. She's a dark side person. So you can do fun little things like this, but the NCO frequency is going to give you the most precise frequency. So in this particular case, when I pass a frequency to it, it will start it up. If I pass 0, then remember what I said earlier, pin clear will turn off a smart pin. And then in this case, because I don't know what the output is, after I've cleared it, I just drive it low to make sure that it is working. Now, here's the thing, again, for those of you new to smart pins, you cannot simply drive the pin low. It will have no effect on the smart pin. In fact, or it'll activate it if it was deactivated. The direction register is what's used as a switch for smart pin mode. So the only way to get rid of a smart pin is with either using WX pin, or in this case, pin clear, which clears all the registers so that you know that they're all zeroed out. And then now, once we do that, pin clear returns a pin from, it takes it from a smart pin to back to a regular tri-state pin, and then pin low. So here's the rules for transmitting a Sony thing. You'll see this is pretty straightforward. We're going to pass it a pin. This is our command mode. Now, this command is the combination of the command plus the address, okay? Even though I'm calling it command, that's a combined thing. So if I'm sending a 12-bit remote code for the 0 button, so pop quiz, what are those bits going to be? I need the Jeopardy theme song playing right now.
I'm going to go with 1001, 1000.
Close. It's going to be 1001 000, because remember the command part is 7 bits, and then it's going to be 10000 because you have 5 bits for the address code. Well, good job.
Come and pick up your parallax hat.
Yeah, Mike wins. So here, this is our command. This is how many bits are in the command. So if we're going to do a TV remote, it's going to be 12. And then count is how many times we want to send that out. And that's going to be 1 to 5. I do throttle that here. So the other thing to remember in our Sony IR frame, that packet to packet is 45 milliseconds. So to remember that. So going in, we're going to mark when we start. And then we're going to, after that, we're going to have a loop that's going to run count times. That's how many packets we're sending out. We're going to turn on the oscillation of that on that pin, on whatever pin we want. Now I've got a constant in the program called IR mod that's set to 38,000. That matches the center frequency of the decoders we have, the demodulators that we have. So we turn it on. Thankfully, Chip gave us a really nice way to delay in microseconds. So we delay, then we turn it off. We wait again for 600 microseconds. And then we're going to, so that is our start bit. Now we're going to send out the packet bits. What we need to do, remember, it's LSB first. So this instruction, command rev 31, will, because everything gets passed in the word. Remember, in the propeller, we're always passing parameters. These values here, those are always words. So I'm taking the command and I'm flipping it over. I'm doing a mirror of it. So what was in bit 0 is now going to end up in bit 31. And I'm not doing it within command. I'm doing that in a temporary variable, and I'm saving it to this working variable called TX bits. So that's what I'm going to transmit. These are my transmission bits right here. And now I'm going to, for every bit that I said I want to transmit, 12 in our case, I'm going to turn on the modulation. And this is a little bit of shenanigans that saves 3 lines of code by doing it in one. This first part here, TX roll equals 1. ROL is rotate left. So that's going to take what's in bit 31 and rotate it around to bit 0. And since I have an equal sign on there, that's going to modify TX bits. Now I'm going to AND that new value with 1. So that becomes my test. So this is called a ternary, it's ternary operator. So if this part is non-zero, we get that. If this part is 0, we get that. So when we have a 1 bit, we're going to take this and stuff it into wait US. If we have a 0 bit, we're going to put 600 in there. So this is a really clean way of grabbing the next bit and delaying for it after we've turned on the modulation. Then we turn the modulation off and wait another 600. So we repeat through all the bits. So now we've done all of the bits, and the last part in there is to wait for the end of our 45 millisecond packet period. So remember, within a frame, we could have up to 5 packets. They're going to be from leading edge of one packet to leading edge of the next packet. It's going to be 45 milliseconds. So this wait count takes the original count, adds 45 milliseconds to it, and then waits there until we hit that time. So this gives us very precise packet alignment. And easy peasy lemon squeezy, we can transmit Sony IR and any codes that we want. And we could actually transmit anything with this. If we align it with, if we do Sony IR rules, then Sony IR devices will respond to it. So this is a simple thing. So somebody pick a code, because this just outputs. And so what I'll do, since I have a logic analyzer hooked up. So right now I've got TV 0. Somebody select another code, because we've been doing all those things. All right, I'm going to select 8 then, since nobody wants to play. So we'll do this. So what I'm going to do is say TV 8. So this is saying use this pin, send that code as a 12-bit value, and do it once. But I'm going to change this to 3 so we can see this. So if I press F10 and F12, so right now it's kind of loaded and armed. What I'm going to do is I'm going to pull up my my logic analyzer. Oh, I need to, sorry, I need to, I can kill this, because this won't work on a modulated output. And I have pin 7 hooked up to the output. You can see I had done a capture earlier. And what I'm going to do is we'll get a bunch of samples. So that's now running, but I have to get this going. And this, oh, doggone it. There we go. So can you see on the screen those packets of 3 pulses? And remember, I selected TV 8 since, so it was the 8 button, and we have to take the button number and subtract 1 from it. So here's 7. So here's a start bit. Here's 1 1 1 0 0 0 0. So there's the code for 8, and then here's 1 0 0 0 0. That's the TV remote. So again, this gray is if we line up in here, you can see, and if we throw the graticule on here, we should be able to. Now, it doesn't snap very well in some zooms, but if we depends on the quantization, but you can see that it says 38.4 kilohertz. Remember, we had told it 38 kilohertz, and I'm not dead on the thing. Again, this is a low-cost analyzer, but you can see there's the modulation, the 38 kilohertz modulation, and there's our bit packets. And by sending this into an IR LED, we can transmit functions. And the last demo takes that code that we just looked at and puts it into its own object. And we have 2 choices. In the case that I was just showing, we're delayed while code is running. But in my object, you can see things look the same. But what happens is when we say we want to transmit, we can, if we want, this code here allows us to put the transmit into its own cog. And so it'll transmit in another cog while we're doing something else, if we want. If we specify no cog, it just calls this code like a regular method, and it will run just like we did a moment ago. You can see at the end of this code, if a cog was used, then it dumps itself. So this is a case where we're using a cog, but only in a transient manner. So when we're transmitting, then the cog is operating. As soon as we're done transmitting, we release the cog to do something else, because IR codes tend to be very transient. We don't need to have a cog operating full time, but you can see this is identical code to what we were doing. And this code then, if we run it, this takes the program number 4, the ability to see what is coming in, and takes program number 7 and sends something out and kind of mashes them together. So if I run this, and what I'm doing is I'm just sending out the button codes, and you can see then I'm getting them back in. So it's better to look at the code. Not a terribly exciting output, but you can see I'm transmitting out the IR LED into the receiver, and then looking at the receiver and seeing my function buttons. So this is not a practical example. It's just a working example, so you can test both sides of the equation. You can say, yep, my IR works and my receive works, and now you can go crazy and do anything you want with Sony IR. Yeah, so I guess that's all I had. So these are, especially for the new people, these are my kind of Johnny Mac reminders as you get into coding. When you have a new program, think about it, think it through and then start it. If you're new to the Propeller and don't know how to write Propeller code, start with a template. Now, I've been programming Propeller for 16 years and I still use a template. It's the best way to go. Use a consistent style. I have a very distinct style. People know it's code that's written by me. You can use that, or you can do your own thing, but be consistent. So when people look at your programs, they know what you mean. Use nice symbol names, use comments where necessary to add clarity to your programs. You'll notice that in the downloads with the code today, I also included the data sheets for the sensors that Parallax provides. Whenever you're dealing with a part, step one is get the data sheet. Study code, you know, if you're getting from somebody else like me or someone else, study the code before you run it. And this is one I added in this week. Read the Propeller documentation for pleasure. It's important just to read through it. You'll find little tidbits that will finally sink in. This happens to me all the time. I tend to go through the documentation that's online somewhat frequently, and I find new things that, oh, gee whiz, I wish I'd understood that in the beginning. You know, we're human. We never will understand anything perfectly the first time, or most of us won't anyway. And so give yourself the opportunity to go through. And as Ken pointed out at the beginning, Jeff's been working on new documentation, so we're going to get some nice formatted stuff, and you know, go through that. Don't make assumptions. The Propeller is a really fun device, especially the P2. I've been proselytizing a lot lately with my friends in Hollywood about switching from the Arduino to the Propeller, because the Propeller is so much easier to program and so much more powerful in many, many ways. And I have a friend, many of you heard me talk about Rick, who's, you know, he's involved in all the Star Wars TV shows right now. And he's getting very excited about the P2 because he uses the P1 all the time. So for those of you that like Star Wars, there is propellers involved in Star Wars now. They're P1s, trying to get the P2 into the next season of things. Anyway, I think I've gone for 2 hours, so it's probably enough out of me, except for questions. I'm happy to answer any question that anybody has.
John, I had a question when you were talking about trying to get the studios in Hollywood or the special effects guys in Hollywood to use the P2. Do those shops adopt like standards that their guys have to stick to when they're building their props and stuff?
Not the shop, the guy. So for example, if you go to Legacy where Rick works, their electronics guy, he's an Arduino person. If you go to Steve Wang's shop where I'm the electronics guy, when they have that need, we're using the Propeller. So it's the guy. Everybody, you know, everybody in the film and TV industry is considered an expert. So you bring your expertise. Now, for specialists like me and that other, you know, whomever is doing the electronics at Legacy, now Rick, he's a mechanical engineer that does a lot of electronic stuff too. And you know, he's one of my best friends. So when we meet, I say, hey, tell me what tools you need for the Propeller so that you don't have to use the Arduinos. And one of them, we're going to talk about in a couple of weeks. We're doing the S-Bus stuff. In the world of animatronics, you know, they use those remote controls to puppeteer animatronics. And back in the old days, we used to write code that would look at the pulses out of an RC receiver and measure them, and then provide that to the program to do something with. With S-Bus, it's nice because we just have a serial data stream that we have to decode. So we have one input to the Propeller and we can get all of these values. For those of you with a good visual memory, that panel, that debug panel that was on the front was showing, you know, you can have up to 18 channels with S-Bus. There are 16 analog and two that are digital, but that's coming in on one pin. And it's updating every 7 to 10 milliseconds. So that's plenty fast enough. So Rick said, hey, I need S-Bus, and I found an inexpensive transmitter receiver combination, and we'll do that. And so, by the way, so for those of you that are interested in all that, you know, when we do that presentation in a couple of weeks, what I'm working towards is getting a graphic output that is not tied to Propeller tools. So I've got some work to do. But this is something I've been thinking about for a while, so that we can move the buttons and switches and knobs on the remote and see it on the screen, and it'll work across any system. That's a personal project that I've been wanting to do anyway.
Can you explain that some more?
Well, I'm going to use processing.
Oh, the software processing.
Yes, because it will take serial and processing was designed for graphical stuff. And so I'm, you know, the nice thing is, so these displays that I do, you know, these kind of things, I do these in a program called Inkscape, which I'm also, you know, a proselytizer for. It's one of my favorite pieces of freeware. It's immensely useful. So, for example, I mentioned my friend Emlyn. Her name is M. Foreign. And so I made her this Star Wars kind of badge that has the letters M4N. This is stainless steel. And I was able to send the Inkscape file to a company and they laser cut this. And she was thrilled with it. So it's a really great program. And processing has the ability to display the SVG files that are created by Inkscape. So my goal is that Ken showed that transmitter is to have a graphical version of that. So when you flip a switch on the physical transmitter, a graphical switch will flip on the screen. That's what I'm working towards.
Are you going to just send a stream of data out to the processing app?
Yes. So every channel will have a value, and there would be a status value too, because what happens with S-Bus, we're kind of getting ahead of our initial presentation, but the S-Bus receiver will say, hey, I think I lost the signal, but here's the last bit of data I had. When it figures out that the signal is really gone, you get another status thing. So you can actually see that. And I have that for the program that Ken showed. It's actually in the forums now. And you can, you know, if you have that receiver and you're running Propeller tool, you can see that. And when you when you turn off the receiver, you'll see the status change from, you know, frame drop to lost signal. So, you know, there's some things to figure out, but I want to be able to, like today's programs were all just terminal text-based, and we've sorted that out a long time ago. So people that are using Macs are able to use, you know, flex prop and with that change, you know, to the, you know, they know what to do. Those programs will work there too, but with a graphical output, I was using the graphical programming or the graphical debug. Well, that doesn't work right now, I don't think, on FlexProp. I have to check with Eric. Anyway, point is, I want to have a really fun time with that. We've got the receiving and the transmitting. So for those of you that remember my friend John Huffman of Johnny Jib, we're going to be doing a program here shortly for another cable operated camera system that uses a prefabricated pan tilt roll device called a Ronin from DJI, the company that makes drones. They also make camera mounts, and you can control that pan tilt roll platform with S-Bus. And so we need the Propeller to talk S-Bus as well, because we also have the ability to control the lens. So the Ronin is only controlling what the camera is looking at. John and I have also developed lens control, so we can control focus and zoom. So we'll have S-Bus output to the Ronin to control where the camera is pointed and how it's configured. And then we'll have focus and zoom controls as well for the lens. So just like with today, where we did receive and transmit, we will do that also with the S-Bus. We want to have both sides of the equation.
Hey, John, I got a question for you. Your prop tool tab stops are different than mine, and I think they're different from the default. So when I'm editing your code on the fly, like today, I got to realign things. Is there a way in prop tool to adapt the settings, or short of that, can you just post your screen of your preferences so I could take a photo of that?
Yeah, get ready. So turn on snipping tool, and I'll do that right now.
Yeah, I'll just take a photo of it.
And I'll post this. I have this documented somewhere, but I change them from time to time too. What am I doing? F5.
Preferences. Yeah.
F5. There we go.
Operation. Yeah. Oh, wow. Okay. So is there a workaround so that when you're editing someone's code, you adapt their settings so that you don't have to find out what, you know, if I didn't have that screenshot, I would have to count out all the tabs.
Yeah, I don't know that there's any way. I mean, they're obviously. We'll have to ask Jeff, because I don't know, to be candid with you, if the smart tab, I don't think they're stored in the file. The file is just plain text, but they're in the editor. So because with Propeller tool, there are no tabs in the file. Everything is padded with spaces. And you can see that by going, if I'm out here, if there were tabs in this line and I press delete, I would get a big jump there, but I don't. So the Propeller tool removes tabs because that would foul up the command things. So you know what? I don't know any way other than manually of going through. Now I've published mine, but I'll do it again if you find it useful. Now, you know, I'm very persnickety about what I want my code to look like, and you may not agree with that. You don't have to. I mean, you can, you know, most of the time objects, even when I use other people's objects, if the object is clean and tidy and I'm not just going nuts because it's not a mess, if it's not a mess, I leave it alone, even if it doesn't meet my standards. But if it doesn't, then I will just go through and, you know, because my IDE is set up for my tab stops, you know, I'll go right through it.
Yeah.
There's no easy answer, I guess.
Since we're on the subject, I have a note as well. There is an extension that will be showing up in the VS Code Spin 2 thing, hopefully within the next month or so. That is also a code formatter, and I'll be adopting those exact same controls that we have in Prop Tool, and you'll be able to set them and configure them, and the code formatter will do that. And it's even selectable, so you can do it on file save. So it'll automatically format your code.
Yeah, that'll be really useful. You know, when I started programming a lot, I was working for Toro and we used Pascal, and there was a guy named Steve who wrote really good code that worked, but it was awful to look at. And I found a thing called Pascal Pretty Printer, you know, that would reformat. And I thought, man, I wish I had that. And I wish I was patient enough to sit down and maybe write a Python program to do that. But there's a lot of work there, figuring out what level is what and where things are, in particular with, you know, a language like Spin, and I suppose Python too, which doesn't have specific markers for blocks. It is all about indenting. I think it's probably easier with block markers to do formatting than it is, you know, than on code like Python and Spin that don't use block markers.
Hey, John, I
Yes,
don't
sir.
know if it helps you any, but those tab settings, they are in the register.
The registry itself.
They're in the registry, yeah, but
Yeah.
but my registry entry is going to be different than everybody else's.
Right. So, yeah, because his objective was, what can I take to feed it into the editor so I'm like you?
Right.
Yeah.
Right. The common way for tools, other kinds of tools to do this, is to record a small, like VI and things like this, will record a small block of commands at the top of the file. And when they see that, they automatically import them and adopt those controls. So there is a pattern for tools doing this. Prop Tool does not, VS Code does not. VS Code could probably be made to do that. So if we thought Jeff wanted to add this in the future, we could make both tools do it.
Jeff has been my friend for a long time, and I already have a very long list of requests for Propeller tools. So I would
Probably not high on the list
file for that. But if that's possible, I mean, you know, you can see one of them in all of my demo programs. I'm hoping that he will do this identifier thing. This is taking a cue from what we did in the basic stamp editor, so that you don't have to save a file and you can do a test compile.
Right.
So he said, yeah, I'm going to do that, but he didn't say how. So I'm going a little leap of faith that he's going to do it exactly the way he did it in the basic stamp.
A nudge in the little
Code I
bit.
have out there with those tags, those P1 and P2 tags will work.
Nice. Yeah, typically burying tags in comments is a typical way to do that. So.
Yeah, but I guess, Stephen, to your point, that actually, you know, there's other ways to do that. But what I mean, I'm really spoiled by the Propeller tool editor because we have tab stops by section.
Sure.
And you know, Jeff and I talk about this all the time. We both use Propeller tool editor for non-propeller stuff.
Cool.
Well, you might want to be using VSC then, John.
I have used it and am using it more because I have some personal projects that I've really for a long time wanted to do iPhone and Android development, and you know, and I just kind of found out just a couple of weeks ago that Google has this tool called Flutter, which lets you have one code base and work on both platforms. And so I've got all that installed, and it wants to use VSC as kind of the outer layer. So I have used VSC many times for C programming and Python programming and even Schmarshmino programming.
Yeah, add my extension, John, and visit my page that tells you whether extensions are useful. And then take a look and tell me what you think as you're typing spin code. It's entertaining. And I will.
I'm always scared when people say, "Tell me what you think," because I tend to not filter myself.
No, I have. When I ask you that, John, I know it's you, and I mean, don't bother to filter. That's what I want to know. The strongest users are also the ones that are most guiding, and so I look forward to what you think of it.
Yeah.
It does offer some differences from Prop Tool, and I also want to add the code formatting so we have that.
Yeah.
That's
That would
basically
be
you type
fantastic.
do a save, and it'll just format it directly. It'd be nice.
Yeah, I would love that if I could take, you know, code, because I have plenty of code from other people that's not formatting to my liking, and I will just manually go through it. I'll make a new copy and go through it because I realize this is a human weakness on my part, but if I look at code that I don't think is formatted properly, it drives me up a wall. And so that's the OCD that I have. Anything else, you know, if you could see my desk, it's a little untidy, but I don't care about my desk. I know where everything is, even if it's untidy, but code, if it's a mess, I go berserk.
Well, we spend years training ourselves to be as quick in recognition and function change as possible.
Right.
And distractors to that understanding what you're seeing is frustrating. It always is. And
Well,
so we develop our styles for that reason.
Well,
Right?
you know,
Remove that.
I may have told this story before, but the other kind of writing that I like to do is film scripts. Film scripts are very technical and have a very specific format. And I got into Hollywood the first time by writing a script, and a now semi-famous actor that I trained with way back when, she asked me if she could read it. And so I was excited because this is a person with some, you know, and 2 days later, when we came back to class, I asked her how she liked the story, and she just ravaged me for about 15 minutes because I had 2 typos. And Hollywood is very, very nasty about what a script looks like, or those kind of bugaboos. In fact, there are these human beings that are called readers that they're the gatekeepers. So whenever I write a script, a reader will see it before a producer sees it. And they're looking for page count, they're looking for formatting. And the reason for that is just like, you know, we do formatting mostly for our visual stuff. Now, in the Propeller and in Python, it's important because of the way we do blocks. But in the movie industry, if you format a script properly, that turns out to be 1 minute of screen time. So we can estimate, everything is driven off of the way pages are specifically formatted, and it affects budgets and everything else. So that's why people are crazy about that. I think that's part of my kind of nuttiness about formatting documents.
Sure.
Johnny Mac, thank
Yes,
you
sir.
for the infrared presentation.
I hope everybody
today.
enjoyed it. I missed everybody. I was very excited to be back today. It's been a long time since we had a class.
It's good to see you too. Thank you.
Yeah, and all John's code will also be turned into a quick bite so we could find it another way. And it seems that we've got all the questions answered here. Hey, John, I was just curious. You said 1,200 feet with that laser tag gun.
Yeah.
And when you power a lot of LEDs, when you send a lot of power through the LED, how do you do that? What's the circuit?
Yeah, we're using a FET to switch. So we have 5 volts powering the, going to the anode of the LED, and we're switching the cathode through a very small resistor with a FET. So we're going, if you look at the LED spec, we're using what's called a TSL 6100. It has a peak current of 1 amp. So we calculate for that. And I think we even push it a little more because remember, we're modulating at 56 kilohertz.
So even using a very mini, like a 50 ohm resistor will do a lot then.
That will. The other thing, remember, that the tagger has optics on it. There's a lens here. So in the tagger, I got to put this so you can see that the IR LED is way back here, and there's a lens here. So we're collimating that output a little bit. So it's not spreading so far.
Yeah.
We're putting it into a bit of a beam. Now it does spread a bit. I mean, there's no way to get it laser focused, but I was meeting with the laser tag owner over this past weekend, and we talked about building a rig to see if we can fine tune that, because the more precise the optics are, we can't do anything else about the power. We're maxing it out. And we're switching it with a FET so that we're not adding any resistance. So we're driving the FET to complete saturation. And like I said, it's actually a 2-stage FET. If you turn on one FET, that does modulation. If you turn on the second FET, that shorts out the second resistor. So if you want high power, you turn on the second FET, that shorts out a resistor, and the first FET does the modulation. So if you want low power, you turn off the first FET, and that gives you 2 resistors in series. It's not a circuit I designed, somebody else did. I put better parts into it, but that was taken from the original tagger. It was, at first I was looking at it trying to figure out what they were doing, and then it made sense because we actually, again, in the tagger we can set indoor or outdoor mode, because when you're playing in a building, you have, you're not competing with the sun. That's why with the IR, with these dudes, and that Sony pulse has that front end pulse. And you'll notice again, if you look in in some of the captures from the receiver, it said AGC. So that long pulse gives the automatic gain control circuitry time to really tune in what's best for the environment. Because if you're outdoors, you're competing with a lot of IR from the sun. And so it has to open up. Indoors, without so much IR, you can clamp it down because you don't want to swamp the circuitry. So these are really pretty smart devices. And I would say any of you that are doing commercial applications, do look at the data sheet because they'll show a little RC circuit attached to the power supply. You want to put that on there. That will make them much more reliable, the operation of these in commercial apps.
Well, thanks again, John. Get yourself a glass of water and take a break.
I will.
And
go get some lunch finally, too.
Oh, yeah. While we're here, are there other topics of interest to people? Chip is here. Any items that want to be discussed briefly?
I could show my test setup for the P2 cube.
Okay. And what else do we have? How to do true random on the P2. Anything else? Chip, did you have any particular topic, or are there any support needs out there?
Well, I have some pictures of the latest Edge that Michael Mulholland sent us this morning.
Okay, all right.
Nice.
Saw those as well. Anything else from anybody? Well, why don't we look at Stephen's test setup then for the P2P2? And then we'll look at the edge new images, Chip, and you can tell us about that.
All right.
Okay. I have, I'm just basically sharing a web page. This is up at my GitHub repo, and I put a link at the initial start of this discussion. What you're looking at here is 6 panels wired together. They consume 8 amps max each, and so I'm actually driving it with a 60 amp 5-volt power supply. And there's our P2 in the corner down there. And when you drive it and specify to the driver that's a single panel, you get the same image shifted down by 1 row as you work your way left across the panel. And so that's what the hardware's working. And so what I found out is that I can drive 1 or 2 panels really well, but 6, my placement of the bits in time is incorrect. And so I'm actually correcting that now. So the next release of the driver will actually respond to the number of panels correctly and display the output correctly. And that's about all I have.
Did you say 60 amp 5 volt? Did I hear that right?
You did.
What does that power supply look like?
That's it.
Just a bench?
That little box
Oh.
in the corner.
Yeah.
So it's a lot of current at 5 volts.
Yeah. Sorry, I just clicked on the picture. Thanks. Why did I do that? I had no need to click on that picture. Let's just make that go away. Yeah, this thing right here, it's a fan. And so when it's giving me the ability to produce that much power, it has a fan on. These things sit, when they're doing like the text display that you see below, they're only drawing 0.3 of an amp per panel. But they can, when I do full white, all the LEDs turned on with no PWM, they will consume about 8 amps per panel. I have each pair of panels driven by 1 set of wires. And so what you've got is 3 sets of wires down to three different things. So essentially each set of wires is doing 20 amps max. I only need 16.
Wow.
So that's how we're doing that. That's just so I can practice driving everything at full rate. When we actually put it in the cube, I'll put a brightness limiter. We'll configure that in the driver so we don't try and draw too much power from our batteries, so they last a little bit longer.
Well, speaking of putting in a cube, I hate to see this demo get torn down.
This one?
Well, yeah, because you have this clock and this scrolling text capability, probably, right? Some
Yeah.
demonstration of the driver that isn't going to be possible when these panels get repurposed.
Well, yeah, this I may just keep this linear cube for a while. Other people can do the cube. This becomes now 64 times 6 by 64 scrolling display now at this point, where my driver is capable of putting scrolling text across the entire thing, or scrolling fields anywhere on it, along with static fields or video fields. We'll be able to do ultimately. So this could be a long display displaying, doing a lot of individual statuses if I wanted to, of various different things around my house. So heaven knows how this will be tested ultimately.
Well, I'm hoping you can come to Parallax 10 months from now.
Yeah, I saw that note. That'll be interesting. And yes, I'd travel with whatever we could. So
Any
that's
questions for Stephen?
Go ahead.
Yeah, any questions for Stephen? Comments? Keep going.
Yeah.
All right, Chip. P2 Edge.
E2 Edge.
You might want to show
let's
these
see.
guys what you just put in shop a few minutes ago.
Oh, yeah. This
Okay.
morning's been crazy. This is like the biggest day of the year here. All these people showed up. Even Michael Summer came by. You know, he's the guy on here, the German guy, and he's driving right now, but he picked up a bunch of walnut wood from me and we planed it. And I have like not itchy, it's like acidic sawdust down my shirt now because that planer just spits chips everywhere. Anyway, then we moved in. Doug Pintack, who we've worked with at Parallax in the past, He's renting part of our shop here. So we moved in a big Haas mini mill 2 and a Haas lathe. And those are getting set up tonight. And then tomorrow, the guy from the factory is going to come out. And so that stuff will be working. I don't have a picture to really share. I just have like it's just in the room, but all day, everything's been opened up here. People have been running in and out and all this stuff's been coming together. I wanted to talk to Michael Mulholland today about this, but we didn't connect. But I'll show you the, let's see here.
Those mills
Show
are
you
supposed
what
to
we
help
got.
us get our own production up to speed because we are perpetually behind with CNC parts.
Nice.
Yeah, we're going to give Doug quite a few jobs to do.
We can show a quick picture of that chip. Here they are.
Do you have a picture, Ken?
Yeah, I just brought it up.
Yeah.
So that's a VF2 mini mill and then a CNC lathe. And I think that lathe has some milling ability as well, doesn't it?
Yeah, Doug wants to put some light tooling in the bay, or not some live tooling, so that he can like cut flats on things. That mill is pretty interesting. It's very simple. It just has this spindle that can feed material, and then it has all these stationary tool rests where you bolt your tool down, your cutters and parting tools and all this stuff. Even like you can just take a tap die and bolt it down, and the spindle can like spin the workpiece into either a drill bit to drill it out and then back it out, and then like time the sequence of the spindle excursion and the rotation, clockwise and counterclockwise to just take a little thread, like a little tap, and thread a hole in something along the axis of the material being cut.
It's like rigid tapping.
So it's actually
Rigid tapping. Yes.
It's moving the workpiece itself, not the tools.
Right. So imagine, you have a little tap tool, a little, looks kind of like a drill bit, but it has these flutes and cutters on the sides.
Sure.
That thing just mounts stationary, and then it moves the workpiece. Like it'll rotate it in, stop, rotate it.
That's wild.
It's really simple the way that thing works, but it gets the Jaws guy is going to be out here tomorrow morning to bring the big machine up, and then also look at the Haas mill, because there's a problem that it won't go up to, it's supposed to be able to do, I think 6 or 10K RPM on the spindle, but if it goes over 4, the whole machine shuts down. There's some kind of problem. It might be a power supply issue.
I think it depends
But
what
in
kind
our
of
shop
tool
here,
you're
we've got all
throwing.
these. Yeah. Doug got that machine. He was planning on putting it into his garage, but it would not have fit. I mean, that thing was way too big. We had to even open the doorway to get into the room. And here we have all these 208 3-phase drops. So it's very easy to hook all this stuff up. And we have air drops in the ceiling. Everything, it was from the tortilla factory. So we're all equipped for lots and lots of power. So it's ideal room for that stuff.
Okay, not to point a gun at your feet and make you dance, but I just ordered 100 of those hoverboard motors. So the clock has begun for you guys to give a useful motor controller, and then Doug will start making the bearing blocks on this machine. And
Right.
hopefully the pieces can come together at the same time.
Yeah, I just, as John was finishing up, I was coding up a little thing to read here's that hoverboard wheel, right? And then the Hall effect sensor comes down here. I have it plugged into a Johnny Mac board, but I've got 5 volts on the red line, ground on the black, and I'm thinking that the other lines are maybe.
Restart your video, Chip. I accidentally turned it off on you when I was trying to
That's what
spotlight it.
happened. Okay.
Yeah. Sorry.
That's fine. Anyway, I'm not getting like sensible waveforms on the scope. It looks like things are blurred. Has anyone ever used the Hall effect sensor on these motors? It doesn't look like you just power ground it and then pull it up.